All right, good morning. So today we're going to work on the first part of section 5.5, zeros of polynomial functions. And so the first thing we'll talk about is evaluating a polynomial using the remainder theorem. And so if you remember, when we evaluate a polynomial, we just plug in a number and see what the output is for that input. And we can do that according to the remainder theorem using division, and specifically synthetic division is really helpful here. So basically it's what we saw before, where if we divide a polynomial f of x by some linear binomial with a leading coefficient of 1, then the remainder is the value of f of k. So let me show you what I mean by that. Maybe that'll make it a little more clear. So use the remainder theorem to evaluate f of x at x equals 2. And so what we're actually doing here is we're finding f of 2 using synthetic division. So here we already have it solved for x. Remember, we were doing that step previously. We don't have to do that this time. It's already done. And so we'll just write that in, all the coefficients, same thing, synthetic division. So this will be 12, 11, 22, 7, 14, 16, 32, and finally the remainder. And the remainder is what is of interest, because that's going to actually be the output associated with the input 2 for this function. So using the remainder theorem, we can say that f of 2 is 25. And you can check that if you want by actually plugging it into f of x. Don't recommend. That's going to be pretty aggravating. So now if you want to go ahead and try one, use that same process to evaluate this function, f of x, at -3. So pause the video and see how you do. All right, so we should have found that f of -3 is actually -412. So I hope that worked for you. We'll get some more practice with that later. So moving on, another theorem is the factor theorem. And we really have already seen this. And it's kind of something we already know, right? There's a direct relationship between the zeros and the factors. Basically, if we have some factor, say let's x minus 2, and then a 0 that corresponds to that is x equals 2. And that's something we really already know. And so now example 2, let's use this theorem to find the zeros of an expression. So let's show that x plus 2 is a factor of this polynomial. And then we'll deal with find the remaining factors later. So the first thing we want to do is we want to show that this particular binomial is a factor. Now you could use long division if you want. I really don't prefer that. I like to use synthetic when I can because it's faster. Again, that's up to you. So I'll use synthetic. You use whatever method you want. And let's see what we end up with. So this will be 1, -2, -8, +16, 15, and this will be -30. So remember the other day we said that, this is a factor if this is 0. So the factor we already have shown is x plus 2, and then the remaining is just going to be x squared minus 8x plus 15, which is the quotient. And so from there, we can find the remaining factors just using normal methods. So I can actually just factor this by finding numbers that multiply to +15 and add to -8, just like we have done a million gazillion times. That'll be -3 and -5. And so then I can write the remaining factors, which would be x minus 3, x minus 5. And now knowing that this is the factorization, I can set this equal to 0, and then, of course, set each factor equal to 0, and I'll find that the first 0 is -2. We have another 0 at 3, and finally a 0 at 5. And so those are all the zeros for this function. And so again, this is just kind of highlighting the fact that division can be a form of factoring, and we can actually factor a higher degree polynomial like this one. If we're given the first factor especially, we can just take what's left over and continue factoring until we arrive at the fully factored form to find the zeros. So if you'd like to try one, I encourage you to pause the video and do that, and then come back and check your answer. All right, so your zeros here would be 2, -2, and -4. So I hope you did well. So sometimes we're not given a factor, right? And so with these higher order polynomials, it's difficult to figure out where to begin if we don't have a zero to start with, because we have to divide first to even begin to factor using our normal methods. So we have a procedure that we can use that uses the rational zero theorem. And the rational zero theorem just states that, if it does have integer coefficients or those whole number coefficients, then every rational zero that could exist takes on the form p divided by q, where p is the factor of the constant term and q is the factor of the leading coefficient. So let's kind of pick apart what that means. So we can write all of the rational zeros for this function f of x by just making a list of all of the possible fractions created with p divided by q. Now, what is p? Well, p comes from this number. This number is not p. The p values come from this number. And so p, all the possible p's are factors of the constant term, which in this case is 4. And we can ignore the sign because we're going to take all the positive and negatives anyway. And so all of the q values that we're going to use are going to come from the leading coefficient and the factors of that. So this is the factors of 2, right? Because that's going to come from here. So we want to use this and this. So we are going to make a list. The factors of 4 are 1, 2, and 4, and the factors of 2 are 1 and 2. And so what we're going to do is we are going to build all of the possible fractions that can be made with these numbers and these numbers. So let's do that. So this will be 1 over 1, 2 over 1, 4 over 1, right? And then we can also have 1 over 2, 2 over 2, and 4 over 2. So notice these numbers are coming from the factors of 2, or q. These numbers are coming from the factors of 4, or p. And so we have all of these fractions, right? Like we have this list of fractions. And from this, we will generate our list of possible rational zeros. And we're going to, I don't want to write that a million times. And I don't think you do either. So we'll just call those PRZs. And let's add one more thing. So it can be plus or minus P over Q. And that's why we ignored the sign when we were finding the factors of P and Q. So the first fraction coming from here is going to be plus or minus 1. Now that's whole numbers or rational numbers, so that counts. The next PRZ is going to be plus or minus 2, and that came from here. The next one will come from here, and that is plus or minus 4. Continuing, we'll have plus or minus 1/2 as a possible rational zero. Notice here, this is 1, and we already have 1 in the list, so we're not going to do that again. And notice here that this fraction is 2, so we already have that in the list as well. So this is the list of our possible rational zeros for this function. All of the possibilities for p divided by q. All right, so now that we can find the rational zeros, let's use those PRZs to find all the rational zeros of this function. So now notice the previous example said find all possible rational zeros. And now this actually is telling us to find the rational zeros. So there's going to be an additional step. We're going to have to eliminate the ones that aren't zeros in favor of the ones that are. But first we're going to list the PRZs, the possible rational zeros. And so the first thing I want to do is I want to find the possibilities for P and the possibilities for Q. So remember, P is just found by finding the factors of the constant term 1, and Q is found by the factors of the leading coefficient 2. And so the factors of P are 1, and the factors of Q are 1 and 2. And from there, we will build all of our PRZs plus or minus P divided by Q. And so these will be PRZs. Let's make our list. This will be plus or minus. Hold on, let's go back and go ahead and list the possible fractions. So this is 1 over 1 and 1 over 2. And so those are our only possibilities. And so this PRZ list is going to be pretty short. So the first fraction gives us plus or minus 1. And then the second is plus or minus 1/2. And so this is the complete list of possible rational zeros. Well, now we have to start checking to see which one is actually a zero. And we're going to do that by dividing. So one possible rational zero is positive 1. And so we're going to see if that is a factor. Remember, that's going to be, it's a zero or a factor if we have a remainder of 0. So again, feel free to use long division if you insist, but this process is going to be extremely tedious and long if you do make that choice. So this will be 2, 3, 3, -1, -1, 0. Bingo. So this is a factor. So let's write the first iteration of the factored form. This would be x minus 1 is the first factor, which I get from here. And then I'm just going to write the quotient, 2x squared plus 3x minus 1. And so this is the first step of factoring this. And from here, you'll see that you can't factor this thing with the normal methods. So what you have to do is you just continue checking these PRZs against this part that you want to factor. So let's check these PRZs and see what's up. So let's check -1. This will be 2, 3, -1, 2, -2, 1, -1. This is -2, so this is not a factor. And then we'll check 1/2 and -1/2. And when you check those, you'll see that neither of the others are factors also. You'll check the remaining PRZs using the same method. And we'll see that none are factors. Right? So what that tells us is that, you know, we can factor this guy or find factors of this guy, but they're not going to be rational, right? They're going to be ugly, nasty zeros. They're either going to be imaginary or have some sort of square root involved that can't be simplified. So what are the rational zeros? Well, the answer to this question is 1 is the only rational zero, not the only zero, but the only rational zero, and that's important. So moving on, you try, use the rational zero theorem, you know, generate your P's over Q's for your PRZs, and then check all the roots to see which ones are rational zeros. So if you're going to pause the video, I encourage you to do that. All right, and then you saw, and I'm so sorry, there are no rational zeros, so none of these would have worked, but you should have continued checking all of them until you discovered that there are none. And sometimes that'll just be aggravating and that'll happen. So finding the zeros of polynomial functions is the next section. So again, we have to implement the PRZs in order to get started here because there are no methods that are the normal methods that we can use to factor this. So let's go ahead and identify P is 1 and Q is 4. And from those, we can generate our factor list. That's 1. This is 1, 2, and 4. So our list of PRZs, and you probably can see now why I broke this into 2 pieces. This work is long and time-consuming and tedious. So this will be plus or minus 1, plus or minus 1/2, and plus or minus 1/4. So let's go ahead and try this first one. Let's start with positive 1. And then we'll determine if this is a 0 and then see what we're working with from there. So this would be 4, 4, 4, 1, and 1. So this is a factor, thank goodness. So let's go ahead and write what we've got. So this would be x minus 1, and then 4x squared plus 4x plus 1 for what's remaining. So now let's see. We can factor this using the normal methods, and that's always going to be what we want to check first before we continue with the PRZs. Or if you don't like factoring in the normal method, you can just use these guys over here to continue factoring all the way to the end. It's just a little longer and more tedious. But using the normal method will determine that, this factorization, that's times 4 plus 2, that's 2 and 2. Then you would split that middle term, and you would discover that these are the factors. And then, of course, just cleaning this up a little, this is a perfect square. So from this, we can determine that the zeros are positive 1, and then we have negative 1/2 with a multiplicity of 2. And we're all done with that one. So the next thing is telling us about the fundamental theorem of algebra. And the fundamental theorem of algebra basically is something we already know. And it basically states that whatever the degree of the polynomial is how many complex roots it has. And so, to put that into kind of what you're used to seeing, this is a degree 3 polynomial, right? Degree 3 tells us there should be 3 roots. And so that's pretty cool. So we'll go ahead and just factor this. Always check that your normal methods will work, because I'm not trying to do those PRZs if I don't have to. This can be factored by grouping. And you'll see that the factorization, and I'm going to skip that here because I'm assuming we can factor by grouping at this point. If not, we can address that separately. So you'll see that this factors into this. And so splitting the factors, we'll have x plus 3 equals 0, which yields a root of x equals negative 3. And here, though, you'll see that we kind of end up with a problem, which isn't really a problem because somebody once upon a time decided to make it not a problem, by introducing the imaginary unit. So from here, we'll end up with x squared equals negative 1 over 3, and we'll take the square root of both sides, and we'll end up with the square root of negative 1 over 3. And of course, we can't take the square root of a negative number over the real numbers, but if we extend over into the imaginary numbers and the complex numbers, we'll see that we actually can resolve this. And the way we do that is by understanding that the square root of negative 1 is equal to I, the imaginary unit. And as a side note, also please remember that therefore I squared is equal to negative 1 from algebra 2. So we have plus or minus I, and then what's inside is positive now, so that's great. And then we can address this. So this would be, if you put this in your calculator to simplify it, you'll end up with root 3 over 3. So this will be plus or minus I square root of 3 over 3. And this is 2 roots, right? There's a plus and a minus here. So there's a positive and negative version of this root. And then this is the other one. So we do, in fact, have 3, but they're complex roots, not necessarily real roots. And so anytime you take the square root of a negative number, it's going to generate an imaginary solution I. And graphically, looking at this, this is your real root that crosses the x-axis, and these are your imaginary roots that do not. And so this is your plus or minus root 3 over 3 up here. And so now if you want to give it a shot, find the zeros of this function. All of the complex zeros, you should find 3 by the fundamental theorem of algebra. So I'll give a second for you to try that one, and then come back and check your answer. All right, so you should have found that your zeros are x equals negative 4, x equals 1/2, and x equals 1. So you see all of these are real zeros, not necessarily any imaginary units necessary, but we'll get some more practice with those imaginary units in class. I'll make sure to choose several problems that let us practice with that. And so hopefully this helped, and I will see all of you tomorrow.